Welcome back. We are going to look at the second order system now. So let me put this as a second order system. Not a big deal. It's a simple system with the second order. So second order system. And we are going to look at how this second order system will respond to an input. Well, first of all, let's write down the second order system. So let's say we have a transfer function GFS, which is equal to B over S squared plus AS plus B. This is our transfer function for the second order system. As you can see, that the power of S is 2, so this is a second order system. You're not dealing with the first order, now you're looking at the second order system. And we would like to put an input of the step input. As usual, it's going to be 1 over S, and the output is going to be CFS. Now, we want to understand what will be the response of the system and look at the behavior of the system when this step input goes in to this transfer function, depending on what kind of poles are going to be generated by the system itself. So first of all, let's say we have a system which will respond, and I can draw the response over here. It's not going to be a very neat drawing, but close enough. And this is the time t, and this is your c of t, okay? So if we have a system in which we have poles on the left half of the plane, we have two real poles. Let me call this whatever, maybe C and a D. It doesn't matter, some numbers, right? On the left hand side, you've got two poles. If you have two real poles, then your system is overdamped. In other words, let's say here is the line that you are trying to reach. It is going to, it's getting there, but it's going to take a lot more longer time to get there, right, to this dotted line. The rise time is going to be very high. Such a response over here, I'm going to label this as an overdamped, okay? So overdamped happens when you have two real poles. That's called the overdamped. Overdamped happens when you have two real poles. Well, what happens when you have an underdamped system? Well, if you have an underdamped system, this is overdamped. Let me write this down over here, overdamped. And I am going to stay within this area because I like to put all of them here. And if it is going to be underdamped, then you will see it will have two complex poles. You see that? This is the real part, the real, and this is your imaginary. So you can eyeball it and see that it's got two complex poles. Here it had two real poles, two real poles, two real poles. Over here, it has got two complex poles. So two complex poles. When this happens, you have what we call as an underdamped system. So let me draw this in the red so that we have a, so the rise time is going to be a little bit quicker. It's going there faster, but it goes like this. It's getting there, getting there, getting there, getting there, getting there, getting there, like this. Such a system is now called the underdamped system. So let me put that here. This is called the underdamped. Underdamped. Underdamped system. So what's happening here is we have two complex poles. This is called the underdamped. Underdamped. Now, when we have two complex poles, we have underdamped system. When we have two real poles, we have overdamped system. Black is the overdamped, red is the underdamped. Now, suppose if we have a scenario in which we have two imaginary poles, how is that going to look like? Well, let me put this in proper format. So here we have two imaginary poles, right? So two poles on the imaginary axis. That means the system is undamped. So this is two imaginary poles. Two imaginary poles. That means it is undamped. Well, what is the meaning of undamped? Undamped means it is oscillating. So let's try to draw that in green, if you will, or whatever this color is. It goes like this, green, and it keeps on oscillating now. So this system is called the undamped. Kind of marginally stable, keeps on oscillating, never comes back to this, never settles down and comes here. So it is called the undamped system. Now there is one more system that we are going to look at, which is going to be critically damped. It's critically damped when you have two poles at the same location, two real poles. So this is called critically damped. This is what we really want, is critically damped, right? So critically damped. And critically damped, you will see is, which color do I want to use? Maybe blue. So you will see that the rise time is pretty good. It just goes, maybe take a hump over here and then come right there. This blue one that you're looking at is called critically damped. Critically damped. Okay, just to cap this up, here you go one more time. This is a second order system, and we have put a unit step function. And if we have two real poles, then this is called overdamped. And you can see it gets there, but the rise time is going to be very high. Then this system is called overdamped. But now if you have two complex poles, then what you have is an underdamped system. An underdamped system is going to go there, oscillate, and then come back to this original position. And then you have what we call as an undamped system. Undamped system means you have two imaginary poles. The system is oscillating, so it could be the marginally stable system. And then we have critically damped, in which two real poles are the same place. That's what we really want. It goes up there and then settles down. So this is called critically damped. This will help you in solving problem number 3, where you can identify critically damped, overdamped. But we are going to look at some specs later, hopefully in the next video, or maybe following that, in which we're going to look at the damping ratio. We are going to look at the settling time, the rise time, the percent overshoot for the second order system. So I will see you shortly in the next video.